really. It's not academic flow. It's like different math for the same thing. Improvement of
Okay, let's finish this, okay?
Let's go.
All right. Last time we need to start electricity, the more fun stuff.
Okay.
Yeah. So we started entropy last time. We said, how do we calculate entropy, right? I don't think we made any calculations. No?
No, we did
We did one?
the ice to water.
Okay, let's start from there. Okay, so what did we say? ds was equal to, or delta S was dq over T over the temperature, like so, right? So it's delta S. And our goal was to get familiar with this equation and how to use it and how to make some calculations. And the first example was, suppose you have ice at 100 grams, melts and becomes ice at, water at 0 degrees Celsius. Okay. And what's the change in entropy? So let's start with the first example. So 0 degrees Celsius, ice melts, becomes water at 0 degrees Celsius, and the mass is 100 grams or 0.1 kilograms. And the question is, find the change in entropy. Notice the temperature has not changed, so this is an isothermal process. So you got this, delta S is equal to dq over T, and so that's 1 over T dq, and so it becomes 2 over T. The reason I was able to pull out the capital T because
Constant.
it's constant. So just Q over T. Now, Q is the heat that was added in order to melt the ice, and so the heat that's added is the mass times the latent heat of fusion divided by the temperature. Divided by the temperature. Okay, so you have 0.1. By now, you might have memorized this number here. It's what, 3.33?
3.33.
Yeah, 3.33 times 10 to the 5th joules per kilogram. And then T, I hope you don't put 0,
Okay.
because
273.
Kelvin. Yeah, so 273.
Minus.
So delta S is 1 T 2 joules per Kelvin, right? This delta S. Yeah, 120.
Yeah.
Yes.
Good.
Is it always like that in the
I think I did.
Yes.
A lot of,
Yeah.
It's always like that.
When you pull out the T, yeah, to go TQ is just the total.
you know,
Yeah.
I read 400. I read 400 like this.
Okay. Do you remember?
Maybe
Maybe if the temperature changes? Good.
Itu soal yang
So
easy.
T is
Tapi I masukin yang keduanya.
So let's do one where the temperature
Oh
changes.
my
That's
God.
my next example. So here's the next one. Next example is this. Let's take this sample of water. Let's say we have water
Or maybe even for more. Because I showed the
at 0 degrees and
Yes.
heated up. So it's water at some T final. Still water. Right? Still water. And it's still 100 grams. So 0.1 kilograms. Okay? And the question is, if the change in entropy is 122, if delta S is equal to 122 joules per Kelvin, what is fine? Find T fine. Is it going to be 10 degrees, 20 degrees Celsius? Is it going to be 90? Maybe 100. Maybe the water has to boil, actually. It's not possible. So let's figure it out. So in this case, the temperature is changing. So we're going to assume, we're going to be hopeful or optimistic and say maybe the temperature when the temperature rises from 0 to something less than 100, the change in entropy will be 120. Right? We just assume that. If it's possible, then we're done. If it's not possible, then we have to revise our assumption. It turns out to be possible, so that's why it was given as an example. So let's try it. So solution. You notice here the temperature is changing, so you cannot pull out the temperature. So let's see how we can deal with this. Delta S equal to integral dq over t. So what do I do here? I want to continue. So what do I know about dq when the temperature is changing? Yeah. It is mc, and instead of delta t becomes dt over t. The mass and the specific heat are constant, so they get pulled out. So now it's possible to do that. Yeah. So what are the limits of integration? What's the lower limit? Yeah. It's the initial, which is
0.
or it should be 270. Yeah, 273. And this one is T final, and we'll get the T final. The answer would be in Kelvin also. So the temperature here is assumed to be in Kelvin. Okay? So do this integral, you get ln. So you get ln of T final minus ln of 273, which is you get the MC in front, which is ln of T final over 273. Right? That's how you combine the ln, right? So on the left side, I have delta S, which is 122. On the right side, I have MC. The mass is 0.1. Now, what's the specific heat? Water, about 4190, right? Joule per kilogram degree Celsius of Kelvin. 4200 about, right? 4190, 4186. So let's just go with that number. So 0.1 times this number will become 419, right? 0.1 kilograms times C, you get 419. So you have 419. And then P final over 273. What's next? I need to get access to this.
Times exponential.
Right, so divide, exponentiate, and then solve for T final. So you get T final would be 273 e to the 122 over 419, right? The exponent. So do that. If you want to do it, I can give you a moment.
365.
How many?
365.27.
Okay, so I will use the 365. Okay. Now you can go back to degrees Celsius, which is
92 degrees.
90. So it's possible. Go to the next things. These were solids, liquids, right? Let's do gases. Let's go back to gases. See what the change in entropy is for those. So, by the way, let me just declare W means W bar, okay? W by the system. So that means for entropy, I need dq over T. But I know from the first law, dE thermal is equal to dq plus or minus W. Minus dW, right? Because W here is the work done by the system. So that means dq is equal to dE thermal plus dW. But dE thermal is mCV what?
Delta. Oh,
dE.
delta. Yeah.
How about dW?
P pressure times change in volume.
or dV. Okay. Pressure is nRT over V. Pressure is nRT over V. So I get dQ and CV dt plus nRT and then over V, so dV over V. So this is my dQ. So dQ over T will be n CE dt over V plus nR. I divide by T so that T goes away. So just have dV over V. Is that right? dV over T. Then we're interested in finding the change in entropy. So delta S would be this integral, right? This integral. This integral. What's this integral? ln again, right? Delta S would be n CV ln of let's say T initial to T final. So T final, ln of T final minus ln of T initial. So that's ln of what? T final over T initial. Plus, for this one, it's going to be nR times what?
ln f VF over V1.
Like this? Yeah. So let's see what the change in entropy for specific cases. This is general, specific cases. Start with, well, the cases we have the ideal gas processes that we go through, the typical ones, right? So first, let's start with the easiest one, adiabatic. What would the change in entropy in that case be? Zero. Because dQ is just zero. No heat is added. Okay? So adiabatic, zero. Let's go with the ones that are more interesting. Isothermal. It's isothermal, it means the temperature does not change. It means the final and the initial temperatures are the same. So what happens? This simplifies, right? ln of 1, which is 0. So this goes away, only this lasts, okay? T final, T initial is 1. The temperature doesn't change. So in that case, delta S is nR ln of T final over initial. Let's go to isochorics. Delta S will be for isochoric. Good. So this one disappears, right? Because V final, V initial are the same. So you just get ln of 1, which is 0. You just get and ln of V final over initial. Good. And then isobaric. That one I will do some side work here. So then you will just write the formula. Okay. Let's do isobaric. For isobaric, I would do it two different ways. The harder way and then the quicker way. Not harder, a little more steps. So I have P final, V final is equal to nR T final. T initial, V initial is equal to nR T initial, right? This is the ideal gas boundary twice. Let's divide the two equations by each other. P final over P initial would be how much?
1.
1, because it's isobaric, pressure doesn't change. So I get V final over V initial on the left side. On the right side, the NR goes away, so you just have T final over T initial, right? T final over T initial. So we have this equality if it's isobaric. So let's go to this and see what happens. Go to this one, see what happens. So I have delta S is equal to NCV ln of T final over T initial plus NR ln of V final over V initial. What should I replace it by?
T final,
Yeah,
T
V
initial.
final over T initial. Right? Now we can factor things. So we can factor, both have N, and then here, ln of V final over V initial. And then what's left inside here? CB. Which is CP, yeah. CP. So, in summary, for isobaric, the delta S is equal to N CP ln of T final over T initial, which is the same as N CP ln of V final over T initial, right? We just said T final over T initial is the same as V final over V initial. It's isobaric. That was the little bit longer way. The quicker way, maybe, is to just go back to here. Figure. So I'm going to do that next. I'll give you a moment to write that chapter. So still doing isobaric, but different way. So here's another way that you can do it. You can say delta S is dq over T, but because it's isobaric, what's dq? And what?
CP.
CP dt. So that becomes NCP, the integral of dt over T, which is natural log, which is T final over T initial, right? It's quicker. And then since T final over T initial is the same as T final over T initial, you get the same. Now it's time to do an example on on one of the ideal gases. And then we will do something more theoretical, and that's the end of this. Okay?
Itu bisa sebut pada. Kalau yang this formula kan volume yang di change to 3 kalau di soal dari volume initial volume tetap no saja.
The example is as follows. Suppose we have 2 moles of nitrogen, and we expand them isobarically. We'll take, so here's the example. Consider 2 moles of N2 expanded into the volume double. It's an isobaric process. Okay? So I'm going to draw the process. Isobaric. So here's V. Here's C. So it goes like this. And this is initial. This is final. So the initial. The final is twice the initial because it doubled. the change? What's the change? Doubles. I'm missing it. Right? So 2 moles of nitrogen, N2, are expanded with an isobaric. The pressure stays constant, but they expand until the volume doubles. So what's the change in entropy there? So how do you expand it? How do you expand something at an isobaric pressure? Keep the pressure constant. So you have think of a piston or a cylinder with a piston, and then what do you do to make the gas expand at a constant pressure?
Heat it.
Speed it up. Yeah.
Heat it up.
Slowly add heat, right? So you allow the piston to move up. What's the pressure as the piston moves up? Just and it's atmospheric pressure, basically, assuming the piston is massive. Okay, so how do we? What's the change in entropy? It's simple actually. Delta S. It's ready to use formula. Here it is. The NCP, natural log of NCP, ln of. Since I have the volumes here, I'll put V final over V initial, right? I'm not told about temperature doubling. I'm told the volume doubling, so I'll just use that. So let's plug in the numbers. What's N? 2. All right, CP, I didn't tell you, but we should know about that. 7 over 2R because diatomic, yeah. And then natural log V final will be initial. That's just the number 2, yeah. So cancel, and you get 7R ln of 2, which is about 40.3. I am going to, can I erase this stuff, the left side? We discuss one more topic. I'm going to discuss that topic twice. One using a sketch, and the other one just using some algebra.
I understood the first one.
I just don't. Dictionary, I don't know.
Okay, so remember the Carnot engine? First of all, remember the efficiency. We said it's equal to 1 minus QC over QH, right?
Yes.
And for Carnot, we found that it's 1 minus TC over TH. How did we find it? We did that cycle, right, that involves 2 isotherms and 2 adiabats. And then we calculated, not calculated, but we found this expression explicitly. What the Carnot engine does, it operates between 2 temperatures, a hot one and then a cold one, right? A cold reservoir and a hot reservoir. And And what it does is it will take heat from here. It will give you work, but it will waste some figure called QC. I made it too small. Okay. And we said for Carnot, 1 minus QC over QH ended up to be this much. Right? And we said this is the maximum and you cannot do better than this. Okay? You cannot do better than that. So I'm going to do one more. This one is going to be sketched more qualitative, and then the next one is going to be more analytical. So this is the maximum, right? So let's say I have a Carnot engine. Here is a Carnot engine. It operates between two temperatures. Here is a, and I'm going to be here is T hot, here is T cold, and our engine, this Carnot engine, let's say it takes 100 joules of QH of heat. It takes 100 joules of heat, and it gives us 10 joules of work, and then it will waste 90 joules. Okay, it will waste 90. Just to come up with some numbers. Just making it up. Right? So some Carnot engine operates at this efficiency. In this case, the efficiency is just 10%, right? You produce 10 joules after you consume 100, so that's just 10% efficiency. Let's just pretend that's the efficiency, and that's it. The Carnot engine is reversible, right? You can do 10 joules of work, you would remove 90 joules from here, and then you will throw 100 joules to the outside. So let's say I use this Carnot engine to cool this room. If I spend 10 joules on it, if I do 10 joules of work on it, 10 joules of work are done on it, 90 joules from this room of heat will be removed, so the room will cool down by that amount, by 90 joules, and then the outside will get 100 joules. So you can run it forward. If it's clockwise, it's what? Heat engine. If it goes counterclockwise, it's a refrigerator. Okay. And the question is, let's say someone comes in and says they have invented an engine that operates between these same two temperatures, but their engine does this. It takes 100 joules of heat, just like yours, it's fine. But instead of giving you 10 joules of work, it gives 20. Give you 20. They say, we made an engine that does this. The question is that possible? And if not, let's try to convince ourselves that is not possible. Okay. So here's how it goes. So I'm saying the claim is this. Someone claims. I'm just giving rough numbers again. I'm not saying these are actual numbers. Just making, for this argument's sake, making up something.
Is the 100 joules is like the heat absorbed, or?
Yes, that's the QH. This is QC.
So we 100 joules of heat entered
Yes.
into the system, and
10 joules of work are done, 90 joules are wasted.
90 joules is like the QC, right?
QC, yes. Does it make sense? So let's say this heat engine, somebody else, says, I will take 100 joules, just like you, but I will do 20 joules of work. And 80 joules are wasted. Okay. I hope, I'm not writing units, everything is joules, right?
Yeah.
Okay. So here's how we show that this engine is not possible. We will this. We're going to do this. Say, okay, I will use your heat engine, the one that you invented, to run my Carnot engine in reverse and see what the consequence is. So I'm going to, you're doing 20, you're saying I get 20 joules of work, right? I'm going to use those 20 joules of work to run 2 Carnot engines and see if that's possible, right? Because each of these consumes 10. I'm going to use 20 joules to run 2 of them simultaneously and see what happens. So here is the sketch. This is TH, right? This is TC. This is the engine that you invented. It's going to take in 100 joules of heat. It will give a certain amount of work, right? And it will only waste 80 joules. So it will give out how many joules of work? So yeah, so I'm going to split it, so 10 on each side, 10 this way, 10 this way. All right, so those are a total of 10 joules of work. So I'm going to use these 10 joules of work here to run a heat engine on this side. So if I run this one in reverse, what do? I will remove what? 90 joules from here. And then I will dump how many joules of heat here? 90 plus 10 is 100. And then the same thing for this one. I run it with 10 joules, so I remove 90 this way, and then I will throw 100 there. So that's the device we have made. You created yours, and I have my two Carnot engines running in reverse, and let's box them. Let's put them in a box. So now this combination needs nothing except for T hot, T cold, just the temperature outside, the temperature inside. You can put them in a box. It's not plugged into electricity or anything. They're just running off of each other. And let's see what the net effect is. Let's see what the net effect is. What's the net effect from here? You remove 90. Throw 80, and you remove 90. So what's the net heat removed from the cold reservoir? It's 180 minus 80. So how many?
100.
100. So effectively, we're doing this. We're removing 100 heats of joule, 100 joules of heat, running in reverse. And then what's the net effect here?
Plus 100.
Just a net of 100. So you just have this perpetual device that just runs, and it just cools this one, and then you throw heat. So the room just gets colder and colder with nothing, with no net effect. So is that possible? No. So that violates the second law. Okay. So meaning this engine is not possible. Let's do some algebra. I think the algebraic method, I like it more than this. Yes.
And the second law, is that the same law that prevents perpetual machines from working?
Well, a perpetual machine could be, I mean, this one you could have an engine just running, like a heat engine in a refrigerator, but the net effect should just be zero. I would remove zero heat from here, and zero heat is dumped here. That's fine, as far as the second law is concerned. But there's always inefficiency and friction, and so in real life you can't make it. But yeah. So let's do, here's the algebra that I would like. Can I erase here?
So this is not possible.
Then I will erase.
Instead of gaining or splitting happen. Doesn't work that way. Harus ada kayak harus lebih kecil karena efficiency nggak boleh 100%.
Let's use the board here. So here is the second law. Delta S for the universe, U for universe, is greater or equal to zero, right? That's the second law. And we said the universe could consist, we could break it down into many ways. One way is to say the system plus everything else, the environment. So it's delta S of the S for system plus delta S for the environment. Zero. E for environment, S for system, and then U for universe, right? Now our system here, this heat engine or Carnot engine, is in contact with two reservoirs. It's contact with a hot reservoir and a cold reservoir. So I can write this delta S of the system plus the environment. I have the hot reservoir and the cold one. So delta S, what did I do to the hot reservoir? How did the entropy change for that one? Plus the change in entropy of the cold reservoir straight away to zero. Okay. Now let's think about what happens over a cycle. Now entropy is a state variable, just like pressure, or volume, or temperature, or thermal energy. When you come back to the same point, what's the change? The change is zero for state variables. So for the system, for the heat engine, after one cycle, the change in entropy is zero. So I'm going to write zero here for one cycle. After one cycle, and then zero. Of course, you're going to run it over many cycles, but after all, the change will just be zero after many cycles. Okay, let's look at the change here for these two. Okay. The hot reservoir. Remember what a reservoir was? It's something so big, its temperature doesn't change. It will just remain constant. So this one will have a Tc at all times, a temperature T cold, and this one will have a temperature T hot at all times. We're going to remove QH from the hot reservoir, right? So what's the change in entropy there? So for this one, the change in entropy is going to be, remember if it's isothermal, like delta S, remember how it looks like. It's dq over T. If T is constant, you can pull it out. So you just have your dq, and so it's just Q over T, right? So from the hot reservoir, we're going to remove QH of heat. So we remove QH. QH itself is a positive quantity, but remove, I'm going to indicate that by a minus sign. And we're going to remove it at what temperature? At T hot. At T hot. And then for the cold one, we're going to what? We're going to add to the cold reservoir, right? We're going to add how many joules of heat? What's the heat added there? What's the symbol? QC. At what temperature?
Cc.
At Tc. Greater or equal to zero. Okay. Let's move this to the other side. So I get this, QC over Tc is greater or equal than QH over TH. Okay? I'm going to multiply both sides by Tc and divide by QH, meaning I will get this, QC over QH is greater or equal than Tc over TH. Okay? Let me just rewrite this one. Okay. Now, I forgot to mention this. If delta S is equal to zero, it means the process